I am Joe Nash. I'm not Rob Whitehead. Unfortunately, Rob couldn't make it here. He has important CTO things to be doing, like building the tech. So they've sent me to talk to you instead. So I'll be here throughout the entire conference. I'm here until late Thursday night. I'll be at the party tonight. If you have any questions about the talk, feel free to grab me after. And we, of course, going to be talking about building simulated worlds, because I can't quite fit the entire title in the schedule on this slide. So simulated worlds, what we're talking about. That's my Twitter handle. If anyone is interested in giving me feedback or in following me on Twitter, please grab me there. So, I want to talk to you. Oh, hello. Oh, I have some incredible lag. Bear with me 1 minute. Okay, cool. So, simulated worlds. What do we mean by simulated worlds, and why do we care about them as game developers? Players are constantly demanding higher fidelity worlds. They want very, very large worlds with high fidelity physics, high fidelity simulations, and they want meaningful interactions. They want the NPCs and the entities that populate that world to feel real, to feel as if the player's part in that world matters. For a long time now, players have been demanding games like this, and I'm sure many of you have grown up and been part of the hype of a game that's coming out, a large open world game that's coming out, and feeling as if you could be part of that world and part of that thing that matters. But we have consistently failed. Well, I wouldn't say failed. Games have consistently underwhelmed and not met expectations of players in providing these worlds. There is always some element or some aspect of the world that shatters immersion in some way or another. Whether that be the simulation isn't quite up to the fidelity that we would expect. The physics are client-side only and not a shared experience in the MMO. Or whether the world is largely static. Or whether some events that we would normally expect to be dynamic and happen on the fly or be simulated actually turn out to be scripted. And as players, when we have those aha moments and we realize that this game isn't quite as immersive as we'd like it to be, or isn't quite as built around us as we'd like it to be, and that we don't actually matter in that world, you have this fantastic moment where you're like, oh, I see. And your connection with that game and your connection with that world is instantly shattered. And I'm sure all of you could tell hundreds of stories about these sorts of experiences. I definitely can, where I've been playing a game which I felt very immersed in personally and felt like I'm being part of that world, and then I noticed something, some crack in the seam or something in the fabric of reality that has made me go, wait a minute, that was scripted. And from that point on, your perception of the game, the perception of the world you're in is entirely changed, and you never quite feel the same about that game again. But this isn't a Gamers Anonymous meeting. We're not going to be exchanging all these tales. But one thing I do want to say about these things is, even though these things happen and even though you break immersion and people detect scripted events, they detect the fakery that you're using to build this picture, to build this simulated looking world, you're still a wizard to the players. You're still doing a lot of trickery and using a lot of your wits. You're being the man behind the curtain to make this seem real, right? Like, you're still having to do a lot to make that world, to simulate a simulated world, essentially what we're talking about. You're doing a lot of trickery, whether that be through networking to make it feel real time, or whether that be on the simulation side, whether you're, for example, my favorite example of this is Animal Crossing, where Animal Crossing is, of course, not running on your whichever console it is the entire time you're playing it, but then when you come back in, it suddenly simulates all these events that have happened in the real world whilst you were gone. That's simulated simulation. By pulling tricks like that to immerse the player, you're being an absolute wizard, and that's great. But what if we could use that creativity, that power, that talent, to actually build the game rather than having to fake the mechanics we want to build? What if the simulation was real and we could actually build the experiences for the player that we want to build? But doing this is very much a balancing act of hardware and resources versus player demands. Building these realistic simulations, these massive, huge-scale worlds with persistent physics, with full persistence of state, is very, very difficult hardware-wise. It doesn't fit on a single machine, and distributed systems are hard. And it's very difficult resource-wise, both in talent and in time and in financials. We can't all afford to go buy our own data center and build our own distributed systems from scratch. We can't all afford the top-tier networking talent who can make these distributed systems work. We can't all afford the amazing programmers who can make these simulated experiences. But players very much want those experiences, which we're seeing played out live on the Steam store. If you look at the success of open world survival games, that is pretty much the demand for open world simulations seen in action. They are bloody everywhere on early access right now. There's like 60 of them. And that is players demanding that these experiences exist. So we want to make that easier for you. And we want to free you from these chains, from having to use your wits. We want to give you a canvas where you can build the simulated experiences that you want to build without having to go for all this trickery, without having to go for all this fakery. You can just use your talents to actually build the game and make the game how you want without having to simulate all these simulated elements. So why do we need to fake it? Why can't we build massively multiplayer, online, fully persistent, physics-driven open worlds? Why isn't that an easy thing to do? And why is this the story whenever you go to any subreddit talking about game development, with people cackling whenever someone said they're going to build an MMO? And that's fundamentally because distributed systems are hard. We're talking about problems which don't fit on a single machine. We're talking about physics of thousands of players. We're talking about simulating the ecology of tens of thousands of living creatures which may breed and evolve and die and kill each other. And you can't just do these things through a simple server-client model. You can't just have one machine sitting under your desk in your bedrooms, streaming to thousands of players. It doesn't work like that, and the networking behind that isn't that simple. And additionally, the content for this is hard as well. If you look at MMOs, they're typically static experiences driven by a lot of static content. You're talking about hundreds of quests, all this dialogue, loads of the static objectives that players interact with, requiring hundreds of content creators. So both from the technical side and the creative side, building large world experiences and MMOs and anything along those lines is very prohibitive to indie developers, to small developers, to cost of developers on a restricted financial means. And because of this, you end up with two different kinds of game. The first is very deep and narrow, where the simulation elements might be very, very deep and advanced, but the breadth through which you can experience them is very narrow. And a really good example of this is Dwarf Fortress. I've been playing Dwarf Fortress now for probably like at least a decade. It's one of my favorite games. And the simulation on this is insane. There's my favorite bug report of all time comes from Dwarf Fortress. I'm sure you've all seen it, where Toady1 had implemented the ability for cats to tread in liquid and then tread that through the buildings. He'd then also implemented the ability for a cat to clean itself by licking its paw. He had then also implemented the ability for cats to ingest anything. So they would tread in beer spilt by dwarves, lick their paws to clean it, get drunk, and then die from intoxication. The best bug ever, and caused by very, very high fidelity simulation. And everything in Dwarf Fortress, every player, every NPC, every entity has history. It has actions that happen to it and consequences that happen because of those histories. But we can only experience it for a very limited window, and we can't experience that whole world in real time. It is a deep but narrow simulation. And on the other end, we have, On the other end, we have broad and shallow. We have simulations which, or game worlds, which are very, very wide in scope. They're very, very large. We can roam them in their entirety, thinking GTA, those sorts of games. You can walk from one end of the map to the other without encountering a loading screen, but the simulation follows you. The world doesn't exist until you're in that part of the world. You often have that fun moment in GTA where you tend to outrun the simulation, and then you're standing there and you're like, there's no cars and NPCs here. And then you see a line of identical cars coming down the road in the distance, like a caravan's been following you. That is a simulation, the bubble of simulation following you through the world. That is a broad and shallow simulation. So in an ideal world, we want to bring these together. We want some synergy between these two things. I'm really gutted I spoiled the synergy gif. So we want a deep simulation, which is very, very broad. We want to experience high-fidelity simulation across the entire world space. And that is when I want to talk to you a little bit about SpatialOS. So I'm from Improbable. SpatialOS is the platform that we developed to help deal with this problem. We started out as a game studio, very similar story to Slack. We started as a game studio wanting to build a game. And the two co-founders, Rob and Herman, had this ridiculously ludicrous scale game in mind that they just couldn't build with any off-the-shelf technology currently existing. So they started developing a platform in order to do that, and it kind of got to a point where they said this could be useful to other developers, and therein Improbable was born. So when we talk about worlds, when we talk about SpatialOS, we're talking about a single instance. Did I say Uncharted? I have no idea what it says Uncharted. That should say Unsharded. A single instance, unsharded world with tens of thousands of square kilometers. So we're talking about like worlds the size of countries, right? And the player should, in theory, be able to walk from one side of that world to the other, and that world should feel alive. It should have full persistence. An effect I make on the world should still be there when I come back later. It should have dynamic NPCs and full physics interactions. We should be able to actually carve our place out in this world and have it make a difference to us as players. OK, cool. And when we talk about SpatialOS, we talk about the entity component system. I'm sure most of you have heard of it. If you haven't, there's actually, handily enough, a talk coming up after this one, after lunch, about the entity component system. It's a really solid architecture. I'll give you the brief rundown, but if you're interested in more, definitely hang around for that talk after. So the entity component system, we talk about entities having components, and those components all have states or properties. And those components describe behaviors or things that can be acted upon. For example, a player may have the ability to move. It may have a physical component. But then so would NPCs. So we can share these behaviors between them. But something which NPCs won't have, which a player may have, might be, for example, a inventory system or a level up system. So you can have components that enable you to have very modular code that you share between multiple entities, or equally you can keep that code restricted. And then the system comes in with systems handle single component types. So you often see this on a single machine architecture with these systems being threads. So you may have a thread that handles all of your physics components. So all of the gravity, all of the movement may be handled by a single thread. Equally, you may have a game logic component which deals with updating your game logic states, such as inventory, such as health, those sorts of things. And those systems then update those states. So the systems will update the states, acting out the component behaviors, and those states will be reflected, and changes to the entities will be made. When we talk about this on a large scale, when we talk about this going beyond single machines, we have to do something a bit different. And with SpatialOS, we use what's called the entity component worker architecture. It's very, very similar, but we just swap that system out with something that's distributed by nature. So when we talk about workers, we're talking about single compute units. We're talking about what could be a container, it could be a whole machine. And these are in a commodity cloud. So SpatialOS runs on the Google Cloud Platform. And we see here that we have our components, like I mentioned before. We could have physics, we could have health, we could have pathfinding. And then we have a variety of workers, very much same as in systems, a variety of workers which manage those individual components. We could have a physics engine running in our cloud. We could have a logic worker, any pathfinding software. And those run on the SpatialOS cloud. And as I said before, with these, so when you program SpatialOS, you do it against our SDK. We provide an SDK that enables you to write against our cloud platform, and it implements the entity component worker architecture. So this is an attack behavior from a demo we have on our blog, which is open source, called Abyssals. It was made in 2 weeks by a single developer and 3 artists who made a massively multiplayer online game very, very quickly, and the code is available on the blog. And this is an attack behavior which is shared between both the player and the NPCs. So we have very modular, reusable code, which can cut down a lot on our development time. And then when we talk about the cloud platform itself, and we talk about these workers, this is where some of the Unity stuff comes into play, which is really some of the really interesting things that happen. So our cloud platform is actually managing thousands of machines and thousands of disparate compute units in order to provide you the full world and simulation. One of these workers that we provide out of the box, although you can use any game engine, is Unity. And when we talk about Unity with SpatialOS, we talk about 2 different things. We have the game client, which I'll talk about a little bit more in a minute. And then we have the worker that acts on the server side in the cloud platform. And you can use Unity for many things. We primarily use it for physics. So if you're dealing with a very, very large world, a very physically rich world, where, say, the main mechanic of the game is to stack bricks and push them around, but you're doing this on a country-sized scale with tens of thousands of players, because who doesn't want to play MMO Lego? Instead of having one Unity instance manage the physics of that entire world, which it just wouldn't be able to do, you can't manage that problem that size on a single machine, we spool up and intermesh thousands of Unity game engines, and they all act on the world in different spatial areas. That world is a large vector space, and each of these workers controls a disparate area, and they manage the physics in that area for the entities within that bubble. And those workers are managed. So they are scaled and made and dynamically resized without you having to worry about any of it. If there's only 5 players playing and they're playing in one corner of the world, the workers in the rest of the world will spool down, and the workers will concentrate on the area where players are interacting. Equally, when another 9,995 players join, workers will spread across the world and they'll scale to deal with that. You don't have to do anything to do with scaling up. You don't have to worry about that at all. It's all managed for you by the platform. And any other worker that you use or build will be managed as well. We'll talk about custom workers in a bit, but you can build your own workers that, say, do AI or pathfinding, whatever, against our C++ SDK, and those will automatically become managed workers, and the platform will be able to scale those and deal with all that scaling issues for you. So when we look at the platform, we get a somewhat architecture like this in this neat diagram, which I plagiarized from our new website build, which hasn't gone live yet, don't tell anyone. So we have this underlying platform underneath, which we call Fabric, and that's essentially managing a fleet of cloud servers. And then you have this vector space here. You see that shaded rectangle. And that shaded rectangle is your world. And then within that world, you might have entities. These are the cubes. And you have multiple workers working in vector spaces. So you see that dashed rectangle in the middle? That's the logic worker. It's controlling logic for that entire world. And it's able to cover a large space because the logic is simple. But the physics could be very rich. So we have two physics workers, each controlling a separate set of entities with some overlap in the middle. And the overlap is very interesting because obviously physics is non-deterministic. So when we talk about that overlap, we talk about authoritative states. So an individual worker has a right ability to a set of states of an entity, and the other worker watches at that point. So there's communication going on between the workers there to make sure that if there's a player under each of those physics bubbles, that they both see the same physics interaction on that shared entity. And one of the neat aspects about this self-managing, about this managed cloud, is that you get fault tolerance for free. Because as I said, we're able to spool up new workers, and we're able to dynamically resize new workers. But if a worker falls over, say a physics worker, an instance of Unity, seg faults, whatever happens to it, it will collapse, we'll automatically spool up a new worker to take its place. And you won't lose any of the state of the object. The player will experience they might experience a couple of milliseconds of lag or delay, maybe a bit of rubber banding, but they won't notice, they won't disconnect. The game will just self-heal and continue on as normal. And you notice there that I said we don't lose the state. One of the neat things about this sort of architecture is you get persistence by default. The state of all the entities is actually managed by the underlying cloud platform, and it's passed to the workers. So if a worker has interest in a physics component, the underlying cloud platform will keep track of the physical states of an entity, and it will feed those states continuously to an individual worker as it needs it. That worker will then act on those states and will update those states and send those back to the platform, which will send them back to the entity. So that way we can actually have behaviors and components acted out while having full persistence, because that worker goes down, the states are actually stored within the platform, not within the individual worker. So we just spool up a new worker and share those states. Equally, if we decide we no longer want to simulate part of the world, we can just spool down the worker, the state is stored, and then later on, when someone comes back to that part of the world and we start simulating it again, persistence remains. Whatever happened there remains. If we have an object there, it can stay there. You can destroy someone's building or base, and the rubble can stay there, and players can discover it like years on and wonder what happened, what battles took place in this part of the world. It enables you as developers to build very interesting mechanics on top of this. And then, so I mentioned earlier that we have game clients as Unity as well. So we have this interesting, doing this way of dealing with the states, of basically having the state streamed from the platform to whichever worker, makes it very easy to do with clients, because clients are just a special case of a worker. Instead of being managed by the cloud platform, they're local. And that means that they're essentially just a worker that's just receiving states. So you can have a client be any form you want. Your client could be, for example, a first-person shooter view compiled against Unity for the Xbox, or it could be a top-down tablet view. You have multiple windows into the same world, as long as whatever you're building for can access the states fed to it by the platform. So you can make games that work across any platform, and not just from the single view, but from multiple views, multiple different kinds of experiences. When we start to get into this, in like the early 2000s, there was a sudden trend for RTS games that had both you playing as the units and also players playing as like the commander on top. Like Savage was one of them. Great games. They never really seemed to catch on. We're now starting to see these sorts of models can be built on a much larger scale and be built to much higher fidelity. And then we also get multiplayer by default, because players or player characters are just any other type of entity, right? They differ in no way from an NPC, except in the components they have and the fact that their states are being streamed to an additional worker. So if you build a game against SpatialOS and you want to make it multiplayer, it's just multiplayer. You just designate players as players. Their clients will be able to receive their states. You can restrict the states that an individual client receives. So obviously you don't want every client to receive every player. And there you go, you just have multiplayer. So we're dealing with a lot of things by default there. You get persistence, you get multiplayer, you get scaling, fault tolerance, a lot of things by default that you don't have to manage. You don't have to worry about any infrastructure. You don't have to worry about any DevOps. You don't have to deal with that. You can get on with building the games that you want to build and the experiences that you want to build without being restricted in any of the surrounding fluff. So let me talk about custom workers. So right now we support two primary workers. That's Unity and what we call the GSIM, so that's a Scala worker. So that's for game logic. It's made to be performant for game logic, so it's very cheap to run on the cloud. But you can build any additional workers you want. So a great example of this, oh no, my GIF's not there. A great example of this is we had someone take Boyd's flocking algorithm, and they implemented it in C++, and then they put that against some bird entities in the game. They had the C++ flocking worker interact with the state of those birds. That was then simulated by the physics worker, and these birds just took flight and just flew in a massive flock. And we had thousands of these birds flying in a flocking pattern just by plugging in a custom worker. So if you have existing components, existing engines, existing whatever it is you want to build, existing middleware, C++, etc., you just plug it into our SDK for the custom workers, and that will become managed on our cloud platform. It deals with scalability for you, as long as it can work on a single entity and behavior. So with that platform, it sets us to overcome both those challenges mentioned at the beginning. We overcome the technical difficulties, and we also overcome the creative. Because if we've got high performance persistent simulation, we can find that we don't actually need as much of the static content. If you look at a lot of the games that are very popular now, like say Gang Beasts, or even some time ago, I'm sure many of you have played Gary's Mod. Gary's Mod is actually how I got into programming, so it's very dear to my heart. We're talking about games that give you very simple physical things and very simple physical interactions, and players are able to create thousands of hours of gameplay just from simple physics interactions. That same principle applies to games on a massive scale. If you look at Minecraft, they've been able to create a hugely successful viral game just by the ability to stack blocks up. But the problem with Minecraft is it's based on single servers, and it's not persistent. Frequently you get server wipes, frequently the world gets completely trashed. But we can overcome both challenges and have a massively scaled world, fully persistent, that has these simple rules that players can build their own gameplay on top of, so we don't need to be driven entirely by static content. And when you look at both those things together, when you look at what comes out of having both those things, we see a very real example, which is Worlds Adrift, which is built on Unity and SpatialOS. And Worlds Adrift is built by Bossa Studios. They built Surgeon Simulator and Iron Bread. And Worlds Adrift is a absolutely massive MMO where you build and fly steampunk-styled pirate ships. I can't think of anything cooler than flying steampunk-style pirate ships. And it is a world that's the size of Israel or Wales, whichever is more relatable for you. Apparently they're the same size. It is an absolutely massive world of tens of millions of persistent entities. There are ecologies of creatures that live and breed. They actually had a fantastic problem where very early on in the development of the game, some of their manta rays, they've got these flying manta rays, started breeding like crazy and would bring down the alphas. So they've got active ecologies of creatures that patrol the lands. They've got tens of thousands of players. You can fly from one end of the map to the other without encountering a single loading screen or separate instance. And they have full physics. All of the gameplay is physics-driven. You build a structure for your ship, and you harvest materials to build components and bolt those onto the ship, and then cannonballs from enemy ships tear through those and destroy those. And once your ship is destroyed, it will stay on a floating island, and the remains will stay there forever until someone else comes through and salvages them. So if you find some far-flung corner of the world, and 5 years later some player discovers your remains, they can harvest and use those resources for themselves. You have full persistence. And this is a very, very small studio. This team was originally 5 devs and 8 creative people. And this is one of the largest, most seamless MMOs ever built. We're a very, very small team on a very, very large scale. So the kind of message I want to get across there is that it is now possible for smaller studios to build much larger games without having to worry about the infrastructure behind it, without having to worry about the technical challenges of scaling these things. And one of the approaches is SpatialOS. And if you have any questions about how we do any of this or about using it, please come and chat to me. I'm Joe Nash, and thank you very much.